Very good evening, Lakshmi. Good evening, sir. So, how are you doing, Lakshmi? I'm fine, okay. Thanks for asking. How about you? Very good evening, Batula. How are you? Okay, then I guess now let's start with the class, okay? So, yes, first of all, good evening, everyone. I hope everyone is doing fine. So, in today's class, we're going to start with a new topic, like in the same unit, as the chapter name is what? Alcohol, phenol, and ether. So, the topic of discussion is going to be the ethers, okay? So, let's quickly discuss about a ether. So, what are ether? That if let's suppose I'm having some ROR kind of thing, so it's a ether there simply. Okay, this is the ether one. So in the ether part, it's not a very lengthy topic like the alcohol. Okay, so very simple topic. In this ether part, we are going to discuss about classification part, physical property part, preparation, then chemical property. So basically, these four chapter topic we are going to cover under the ether there. So let's just start with the classification first of all. So we have to classify the ether into the two part. One is symmetrical and one is asymmetrical ether. So what is the meaning of symmetrical and asymmetrical? So let's try to understand. For example, if let's see this is oxygen, okay, this is the identity of this group. So this is oxygen. Let's suppose this is a CH3 and a CH3. So both side we are ended with the same group side and CH3 this side. So it's a symmetrical ether. Like symmetry is maintained. Okay, I hope you know what is the meaning of the symmetry there. So it's a symmetrical ether simple sorted. And see this, look at this like a symmetry. The same CH3 this side, same CH3 this side. Okay, then what if this is oxygen there at this side? Let's suppose this is a CH2 and this is a CH3. Okay. Or look at this. It's a CH3 there. So if in this case, if you're observing something, this side there is a two carbon. This side there's a one carbon. And in this case, if we are checking for the symmetry, there is any kind of symmetry there? No, symmetry is not there. So the second type is known as a asymmetrical, or you can say unsymmetrical ether. So it's a unsymmetrical. It means symmetry is not there. So like I maybe you already know. If you don't know, I hope this point is now clear for everyone. Very good evening, Harika. Okay, so this is normal, that is symmetrical and asymmetrical, or unsymmetrical ether you can say. So let's just back again where we are just discussing about this, that the ether part here. So let's just back here. Now observe this. What is symmetrical or simple? Like both the group same, but in this case the group may different group have to be there. Now let's discuss about the nomenclature, because nomenclature is very much important, and I'm assuming some of you already forget about the nomenclature of the ether especially. Okay, so let's find out the name for this compound. Okay, the symmetrical one. Anyone? What is the name for this given compound? Yes, please. Sorry. Tell the name to answer this, please. Methoxymethane. Okay. Methoxymethane or methoxyethane. Okay, Shiva. Okay, so yes, very good. You're right. So what is the answer for this question? See, basically, like, how to give the name. First of all, we have to identify the parent chain. In this case, there is not an issue like parent chain is there or not. So observe this. Simply, you can say, with respect to this is my methyl group. Okay, so I have to use meth for this. But, oxygen is also present there. So with respect to the oxygen, we are going to use methoxy. And then one more methyl is there. So it's become methoxymethyl. Sorry, methoxymethane. Okay, so this is going to be the methoxymethane there. Then how about the second one? Like in this case, there's a two choices. Okay, how about the two choices there? For example, I can say that maybe this methyl is the part of the oxy. So the condition number one, we can say it is going to be the methoxy. Like uh, wait, maybe that this oxygen combined with the CH3 and the second one is going to be the ethane part. So this is a condition number one. Or the condition number two, that no, maybe that this oxygen is going to combine with this part here. So means it's become what? It's a ethoxy, okay? It's a ethoxymethane. So now my question to you basically, like how to identify which name is correct. Yes, Shiva, do you know the reason? Because you already answered the question. Why not ethoxymethane is the correct answer here? I hope it's visible now. Yes, please. Anyone doing the reason behind this? Yes, of course. We have to consider that chain as a parent chain in which we are having a maximum number of carbon. So look at this. In this case, this is 1 and 2. It's my parent chain. You know how to give the naming. Like this is my parent chain and it's a substituent on the parent chain. So you know how the name. First of all, substituent part, then the parent chain. So that's why the name become methoxy and then ethane. Okay, so very good about this. So that's it. This is all for the case. But now okay, this is a IUPAC name, but here in the reaction part, most of the time we are using common name. Common name means that, for example, in this case, what is the name for the compound? The name is very simple. How many methyl is there? One and two methyl. So the common name is really simple. That you can simply say it's a dimethyl, and for this one we are going to use ether. So it's a dimethyl ether. Or for this one you can say one and two. So it's become ethyl, methyl, then ether. Okay, I hope you know the alphabetical order. That is first of all ethyl, then it's become methyl, and then it's become ether there. So this is a common name. So let's see a kind of table there. Look at this here, both kind of name is present. It's a IUPAC name, like as we discussed, CH3COCH3. Okay, methoxy methane is the IUPAC name and the common name is dimethyl ether. Okay, for this one, like look at this, one carbon, two carbon, three carbon is there. So the parent chain is what? Three carbon one. So it's become one methoxy propane. Or you can say methyl n propyl ether there. Okay, it's better to mention an n methyl, sorry, n propyl. You can omit n as well. Okay, but better to use so that we can get a good idea like whether the kind of branching there or not. Okay, look at the next one. See this. Okay, this one, I'm, wait, let me just draw the next slide. CH3CO, CH2. Okay, so it's a C6H5O, CH2, CH2C, CH2, CH2, C, and 2CH3. Okay, so first of all, please answer the question, what is the IUPAC name for this compound? Okay, IUPAC name. Like which one you have to consider as a parent chain? Okay, very good evening, Aman. After so many days. Straight chain. You mean to say straight is the parent one, right? Benzene is the parent. Yes, very good. Benzene is the parent, right? So can you just tell me the reason as well? Okay, benzene is the parent, but how the benzene is the parent? Why not the straight chain? Three methyl butoxybenzene. Very good, Lakshmi. Okay, more carbon atom. No, actually the carbon atom, like if you're observing one, two, three, four, five. Okay, uh, you know the rule is what? Unsaturation. We have to give the most priority to the unsaturation part here. Okay. No, see, number is the only issue when let's suppose that if the carbon is different. Simple, just try to understand what I want to highlight there. First of all, unsaturation got the first priority over the number of carbon. So in this case, number of carbon is not the issue. Like it's just a coincidence, like this is a six carbon and it's a five carbon system. Otherwise, the only reason we are selecting the benzene because the unsaturation present there. Okay, what if let's suppose there is a seven carbon, okay? What if let's suppose one more CH2 and CH3 group is there? Still, the benzene is going to be like a parent one. Okay, I hope the point is clear for everyone. Okay then, so let's see that how about the naming there. So in this case, you can say this is my parent chain, okay? This is my parent chain. And with respect to this, now this is oxygen. Then how the numbering starting from here? You can say it started from this is the functional group. So it's a one carbon, two carbon, three carbon, and four carbon, right? So it means at third position, which kind of group is connected? CH3. Okay, now one more, maybe one more type came in my mind, ma'am. See, why not you are just starting from one, two, three, or four? Okay, anyone? Why not the red color numbering is correct one here? Why only the blue one is correct? You know the ether priority in the table, the functional group table, or not? Okay, although you're right, but anyway, let's check about the substituent. So first of all, ether is not a type of functional group. Okay, are you getting my point? We are not considering the ether as be like a very supreme kind of functional group. Ether is just being like a substituent only. Just check it the table. Maybe you already know, or maybe you don't know about this. That NO2 group, okay, or ether group, that at the very end of the priority table. Okay, even after the halogen as well. So we are just considering them just like a substituent only. Okay, here the priority is not basically given on the number of what, that is the, you can say, a functional group. The reason is not the functional group. Okay, yes, you're right, Batula. So let's see actually what is the reason behind this. If you're observing something here, look at the numbering. It's a 1 and it's a 3. In this case, how much numbering we are end up? Like 1 plus 3, we are getting 4. And according to this numbering, look at this. According to this red one, that the substituent at second position or the fourth position. So you know, you remember that the lowest lock and sum rule. So it's a sixth. Six is the number. So that's why the red numbering is not the correct one. Be noted again, ether is not that supreme kind of functional group, so it's just being like a substituent only. Okay, so that's why the blue is the correct one. Anyway, so let's see now what is the numbering here. At third position, we'll be having methyl. So it's become 3 methyl. Okay, and then how many carbon? That is a 4 carbon. So it's a but. Okay, but so the parent chain is the benzene, so the oxy part is go with the butane. So it's become butoxy. And then it's a benzene there. So this is the name. It's become 3-methyl butoxybenzene. Okay, so I hope the name is clear for everyone. That's it. This is how we're giving the normal like IUPAC name nomenclature. So let's just back again. Some you can try. Okay, so now let's drop this now. So let's see some more important point here. Look at this. What is the name for the common name? Common name. Okay, so the common name for the common one, it's simple. That you know it's a phenyl part. Phenyl. Okay, and this we already discussed so many times. Look at this. This kind. What is it? Iso group. It's an iso group. So it's become phenyl isobutyl, okay, and then ether. So this is the common name for this one. Phenyl isobutyl and then ether. Okay, so let's just back again. This is written already. Look at this. And now how about this case? So in this case, like it's a 2-ethoxy, 1 dimethyl. So in the numbering starting from here, 1 and 2 there. So it's become simple 2-ethoxy, 1 dimethyl benzene there. And for this one, why nothing is present there? Because the IUPAC name is the common name here. Okay, so that's why, because it's a kind of substituent kind of thing. So that's why we can't use direct name. So what will be the IUPAC name? This is the only common name here. And for this one, like 1,2 dimethoxy and then ethane. Okay, okay. Let's just discuss this on the next slide. Okay. So wait. Sorry. So in this case, what is this? It's a CH2. It's a CH2 and it's a OCH3 and a OCH3. So for this one, how about the name? You can say one this part, one this part. So it's become dimethoxy. Okay. So it's become dimethoxy. Dimethoxy, and this is a parent chain. It's become ethane. So that is the case that we discussed in the slide part. So let's just back again. I hope this point is now clear. 1,2 dimethoxy, you know, I missed the numbering, so just go with the numbering as well. Okay, so this is all for the kind of table there. That's it. This is all for the nomenclature, the basic introduction of the ether there. Now let's start with that the chemical reaction or the physical property. Let's just see again what we're discussing. So this part is done. Classification part is done. Now let's talk about the physical property first of all, then chemical property, and then preparation part. Okay, sorry, the cycle is different. First of all, the classification, and then preparation, then chemical property, and then physical. Okay. So right now we're discussing about the preparation of the ether there. Okay, so it's a really interesting topic. Dehydration of alcohol. Okay. So now listen, it's really much important topic, because here, if you to change the temperature, we are end up with a different product. Okay. For example, a general question for you. Just try to answer the question. For example, if let's suppose this is a CH2 and this is a CH2 and this is a OH. Okay, let's say the CH3. Okay, one more carbon, CH3. Okay, so in this case, I'm asking a very general question to you. We are using acid. You know, acid kettle, this is kind of reaction because H positive take the, sorry, the oxygen has a lone pair, take the H positive and from the H2SO4. We already covered this dehydration topic so many times. Okay, so H2SO4, again H2SO4, again H2SO4 there. So it means something is different for the different kind of cases. Yes. Now listen my point. Let's suppose this is a case number A, this is a case number B, and this is a case number C. Okay. So in this case, you will tell me, what if I'm using a low temperature? Okay. So in this case, there is a two kind of possibility there. There is a two kind of possibility. What is the possibility number one? Okay. So the possibility number one, maybe we are getting this is a CH2, CH2, CH2 and O, and a CH2 and CH3, CH2 and CH3. Okay, wait, like this. It's a ether formation. So if I'm using low temperature, the condition number one, maybe we are getting this kind of product. Okay, or if let's suppose I'm using a high temperature, so one more possibility have to be there, that it's a CH3, CH2 double bond and a CH2. Okay, maybe you're not getting my point. Wait for a while, I will explain what I want to ask to you. And this is a CH double bond CH2 there. It's a condition number B. So now if I'm using low temperature, so according to you, the A is going to be the correct answer, or C is going to be the B is going to be the correct answer. Okay. Yes, Batula. CH3U and then CH2 and then O. Then you can go with the which part? Alphabetical part. Okay. So in this case, you can go with the alphabetical part then meaning. The center one is still going to be the parent one. like methoxy, and then it's become propoxy. So the number alphabetical wise M come first, then prop. Okay. Yes, please. Okay. A is substitution or elimination reaction. Very good evening. Okay, Navi. Yes, please. Ether will form. Okay, Mini. So yes, for the at the low temperature we're getting ether, and a high temperature we're getting a double bond. But I want to simply ask you, what is A? Options are: is it a substitution reaction or is it a elimination reaction? You know, why I'm mentioning the temperature, it's really much important part here. Uh, Ramya, you can say, but now it's open for everyone. If you want to join, you can come. Substitution, very good. Okay, if you remember, it's again the part of the reaction mechanism we discussed so many times. Like if let's suppose you are using a low temperature, so we are going to follow the substitution reaction. If you're using a high temperature, we are going to follow the elimination reaction simply. Okay, so that's it. Now, let me just write a different kind of product, and it's really important part. I'm repeating again and again. Okay, so just for this part only, I'm removing one carbon. Okay, so that because we are having a less space on the slide, so I'm using CH3 only. Okay, CH3 only. So now for a different temperature, temperature is really much important part of this case here. Okay, so the condition number one, that the temperature part, if the temperature is 100 degrees Celsius, very low temperature. Okay, so now acid decide why not I can combine. So in this case, what is the extra part there? That this is a CH3, it is a CH2, and this is HSO4. This is a condition number one. 100 degrees Celsius, or you can say in term of Kelvin. Okay, don't say ma'am, it's written in a book be like Kelvin. So you can use the Kelvin as well. Kelvin wise is a 373 Kelvin. Okay, the second condition, if I'm using 140 degrees Celsius as a temperature, okay, or the you can say according to the temperature wise, it is going to be the 413 Kelvin there. Okay, so the low temperature is not that much high there. In this case, what is the second product we are end up there? That ether, CH3, CH2O, CH2 add CH3. Okay, the condition number three, if the temperature is 170 degrees Celsius, or you can say that how much, 273, 223, no, wait, 273, so it's a 3 and then 4, and okay, 444, so it's a 444 Kelvin. If you're using this temperature range, 443 Kelvin, so what we are getting, that elimination product here. Okay, so this slide is really important. This question asked so many times in a JE as well if you're solving the PYQs, that temperature. If 773, you are end up with the HSO4 addition, and if temperature is 413, that is substitution is going on, and if 170 degree, so it's become double bond. Okay, so this is how the reaction followed here. It's really important reaction again. Okay, yes, thank you so much, Mani. No, it's not possible that Rajput taken some gaming. Okay, Navish. Okay, I'm sorry for this. It's not possible. Okay, as we already discussed this in the group, maybe some videos available in your what SD card. I don't know about that. Okay, sorry for this. I don't know about this. So let's see now. Okay, so now in this case, do you know what is the problem with the method? Anyone? Any problem? You are observing in this method. Okay, so first of all, let me just highlight which step we are going to use basically, right? So this is the only step, this the temperature when we are getting a ether there. But in this case, there is a problem. What is the problem? The problem is really very simple. In this case, we are getting only symmetrical ether. Because every time, look at this, if this is a CH2 CH2, so both side the CH2 CH2 part is connected. So what is the case in this case? Okay, add to the link in the class and ask them to join here. Of course, okay, it's not an issue at my side, okay. So is this point clear for everyone? In this case, what is the problem? Problem is very simple, that we are end up with the symmetrical ether. Okay, so that's why we are avoiding the use of this method. And even you are observing there's a different temperature as well. So now one of the famous reaction as well. So let's just back again what we are discussing there. So yeah, of course, look at this. So this is a temperature point. One more you can add as well, that HSO for addition part. So it's a 443. So high temperature. So we are going to follow the elimination reaction. Be noted, everyone. And if the temperature is 413 Kelvin is there, so we are going to follow the substitution reaction simply, okay? So the substitution and the above one is the elimination reaction there, okay? So now, as we already covered, that in this reaction, what is the problem? We are end up with only the symmetrical ether. So that's why we are going to follow a new reaction. This is known as a Williamson synthesis reaction. Okay, so what is the general point here? Like you are having some Rx, okay, although let's just wait, I will explain the mechanism as well to you. Just try to understand actually what is going to happen. Okay, so you're using some Rx group. Okay, some kind of Rx group we are having, and some kind of ROH group you are having. You can say, okay, RON or like simple RON is there. So basically, what is happening in this case? This part simply combine with this. Okay, it means there's a ROR plus NaX form. First of all, this is a general reaction for you. Now, this reaction going to follow the SN2 mechanism. Be noted, in this case we are going to follow the SN2 mechanism. It means be noted that only the less bulky substituent is going to participate. Okay, we are not going to use the bulky group here. Now the next question between A and B, according to you, which one is a nucleophile here, A or B? Which one is going to attack? Some from side from my personal note and some from, yeah, you can say, okay, Ramya. Right now, please drop, okay? I'm not kind of the person to answer this question, so please avoid all these things and focus on the class only, okay? B. Okay, so very good, Mini. So Lakshmi, that what you're observing, you guess B. So let's see what is the correct answer then. Okay, so look at this. What I'm asking right now? Which one is the nucleophile here? So obviously, see this negative charge. You know the nucleophile is what? Electron rich pieces. So it means in this case, if this is oxygen, it is combined here, and it means this X is going to leave there. Okay, so it's a nucleophile. The answer for this question is what? B is the nucleophile. So let's discuss about the general mechanism for reaction now. Okay, so let's talk about the mechanism part here. This is a kind of example. Like this is a CHCH3ONA and this is a CHNBr, and then we are end up with this kind of product here. Okay, sorted. Now let's talk about the mechanism part. Okay, so let's just discuss about the mechanism part. So how about the mechanism? I have to write it's a SN2 mechanism we are going to follow for this reaction there. So look at this. Any example? Oh, let's see. This is the case. It is a CH3 and it is a CH2. And let's suppose this is a hydrogen and a O negative there. Okay. And this is some kind of C and there is some living group connected here. Okay, let's connect some X group. Okay. So any halogen you can consider. So this is X. So simple, what is happening? This oxygen attack here, this X is going to leave. Okay, it's a single step reaction because it's a SN2 reaction there. Okay, so in this case, then what we are getting, that Na combined with X, it's release NaX, and then we are getting it as a CH3 and a CH3 and this carbon combined with this. Okay, let's consider this as a CH and CH. So basically CH3, better to write the CH3. Okay, so this is normal CH3 there. So this is the answer we are getting now. Now, SN2 mechanism. I hope reaction is clear for everyone. Now, please answer this question, okay? I want to ask a question to you. Okay, okay. So is this reaction feasible or not? In this case, we are going to follow the Williamson synthesis or not. Yes, please answer this question. And if not, then what is the final product? No, right? I guess it's a repeated part, okay? Sorry, I'm not aware about this. That is a Makrala, okay? Or I guess your name is Kavya Shudha. Okay, Kavya Shudha. I'm not aware about this, but according to me, it's not happening right now, okay? I guess you are the new people here, right? So look at this. In this case, this is be like, oh, I am a nucleophile. Be ready. Now it's going to attack. But see, what is it? It's a bulky group, you know. And the SN2 mechanism be like, hey, SN1, SN2 is going on, then how you can attack on a bulky group? So it's not really feasible there. So then, in this case, there's one possibility left. Then nucleophile be like, I am going to take something. Then carbon and hydrogen be like, they decide, okay, just do what? Take one hydrogen. Okay, because you are a nucleophile and we are a bulky group. So the this same nucleophile now attack on a hydrogen, and in this case it's living. It's alpha and beta. So what is happening? It's a alpha beta elimination is going to happen. So be noted if your alkyl halide is bulky. So in place of the ether, we are getting a double bond. Okay, so what is the final product? That is, it's a CH3 and a carbon double bond, and it's a CH2 there. Okay, and one more CH3 is connected. Okay, so this is the final product for this question. Okay, so this is all for the Williamson synthesis there. Now let's back again what we're discussing. So the mechanism part, this is the mechanism if you want to note it like in decent way. Okay, so this connect here, Brahmin leave, and we are going to follow SN2 mechanism, single step mechanism. This is okay. So now please answer this question. Okay, answer this. This question have so many trap. Yes, Abhishek. But just identify the right one. You have to identify the major product here. A, B, C, O, D. What is the major product? You know, here you are going to decide which one is a electrophile, which one is a nucleophile, which one is a living group. Okay, there is a hint. Check it for the living group. Maybe little bit you know the answer then. Okay, and some option you can eliminate it just by common sense. Okay, I guess A. Okay, okay D. Okay A. Do you know if you are saying option A is the correct? Okay, not an issue. But if you are saying option D is the correct, so it's a major issue with the concept. Okay, so let me tell you why. So look at this. First of all, this is a OH. Okay, you are saying option D is the correct here one. Okay, do you know what is the main logic here that iodine come into the picture and okay attack here and OH group is living? It's not possible. We discussed this thing so many times that direct breaking of the bond between carbon oxygen bond, or not this case, that if something is connected with the benzene, so it's really much difficult to break this bond, whether the carbon oxygen or any bond can be there. Reason is what? sp2 hybridized, there is a partial double bond. So then how the option D is the correct? Like it's a illogical answer if you are answering. Okay, so common sense wise, it's not the correct answer. Okay, so let me just remove this. Option D is not going to be the correct answer. Okay, now the choice number two. So in this case, you know who's the main hero of the story here? Look at this. This is the main hero. Because why? Because this one is basically have a living group. Okay, so means you can say this is a C2H5 and this is ready be like I'm having a living group, just attack on me. And now you have to decide, like here, that OH is also present. Okay, so OH is also present. Oxygen has a lone pair. Condition number one. And this one also has a lone, the negative charge. Okay, so this is also this is being like a nucleophile, or as well as this is also being like a nucleophile. And now you will tell me, let me just check this. If this is my A or this is my B, according to you, which one is a better nucleophile? Wait, let's consider the blank slide. Then maybe you're getting my question. See, this is a C2H5 and this is I negative. Okay, condition number one, that this is a OH phenol, or the condition number two, O negative C2H5. Be noted, we are following here, that is a Williamson synthesis. Definitely the mechanism is going to be the SN2 mechanism. Okay, so this is the thing, this is a living group, which one wants to leave there. Now you have to decide between A and B. Okay, this is my A or this is my B. So which one is a better nucleophile? Yes, please. And this is the only thing that cover the answer for this question properly. Yes, please. So yeah, okay, Abhishek, you changed the answer now. So which one is a better nucleophile? Come on. Two things. First of all, one has a negative charge and one has a lone pair as well. Better nucleophile, A or B? That's why organic chemistry is interesting. Okay, okay, Lakshmi, listen my point, everyone. Okay, so first of all, what is nucleophile? Nucleophile is a thing, sorry, that which one has a the donor tendency. You know, charge is the reason of the sorrow. Here you are having a negative charge. So O negative be like, I am behaving like a better nucleophile because you are having a lone pair only. You are neutral, but I'm not neutral. I want to neutralize my charge somehow. Point number one. The point number two, that if this is attacking, what is it? It's a SN2 mechanism. Isn't the benzene ring behaving like a bulky group here? Okay, because see, there's a one carbon, two carbon, total six carbon, but it's a very small group as compared to the benzene ring there. So there's a 2 point. First of all, the bulk here. The second one is what? The nucleophile as well. Okay, so yes, option B is the correct answer. Okay, so it's really important question, and obviously the all the questions so important. Okay, so what is the correct answer for this question? That option number B is the correct answer. Okay, I hope this question is clear for everyone. And if you're having any issue, please let me know. Okay, so that's it. Now let's talk about some physical property here. So physical property, like the typical thing, appearance, ether are clear colorless liquid. Okay, and very good solvent in the laboratory. And odor wise, ether are having a sweet smell. Okay, and very good that and anesthetic reagent as well. Okay, so sweet smell obvious, so that's why better anesthetic agent you can say. Now, how about the boiling point? That typical thing. You know, the branching is there, boiling point is less, and the surface area is more, so boiling point is more. So let me just quickly write that how the boiling point related with a different concept. Okay, then we are comparing with the alcohol, of course. Okay. So first of all, listen my point, that we are discussing about the boiling point. Okay, boiling point is directly proportional to the number of carbon. Okay, number of carbon. The second one, it is directly proportional to the molar mass. Okay, so obviously that more is the mass, more will be the boiling point. It's directly proportional to the surface area. Okay, so in a bracket, let's write that is a straight chain. That if you are having a straight chain, so it means Okay, straight chain there, and then inversely proportional to the branching. Okay, so first of all, this is a basic point that how the boiling point connected with one another. Now, you have to answer the question. If I'm comparing alcohol and ether, which one has a maximum boiling point? Of course, Dashika, I will explain. Okay, so listen my point. Okay, just hold on for a second for a boiling point. Listen, Dashika, that listen, this is a normal phenol. Okay, first of all, this is a phenol. And here, this is a C2H5 and iodine this is okay. And in this case, this is a C2H5 and O negative. Right. So obviously it is behaving okay, this is the kind of you can say nucleophile. Nucleophile is there. Okay. In this case, the thing for which we are checking for attacking reason at every point, that is this. Okay, let me just write a general point at the very bottom so that you can get my point. Right now, what we discussed that you are having some RO negative and A positive. Okay, there is a some RX there, and then there is a formation of ROR. Okay, or this NX remove there. So look at this. If it is mentioned here O negative, so it's totally understood that is it's a Na positive. Okay, Na positive. Just this is the case. So first of all, look at this. This is my living group. Okay, iodine is a living group, like this XX part. Okay, Dashika. Now look at this. That in this case, there's a two choices. The choice number one, this one has a lone pair. Maybe this is also being like a nucleophile. Okay, so it's be like, ma'am, how to decide? Look at this. This is a O negative charge. So this is a better nucleophile here. This is a better nucleophile. Why this is a better nucleophile? Because if you're checking for the nucleophilicity, nucleophile is what? A donor only. So what is the meaning of donor? Donor is that species which one has a negative charge. Okay, so for example, if let's suppose I'm having O negative, so it's a better nucleophile over the OH group there. Okay, reason is what? Because negative charge. This one wants to neutralize negative charge. Okay, so that's why that not this phenol is going to attack here, only which one is going to attack? This is going to attack. Okay, so it means simply, let me just write the reaction at the here, okay, the same reaction. So what we are observing, this is a C2H5 and O negative. Okay, plus this is a C2H5 and I is there. So means that what is happening? That C2H5 and a O and a C2H5 release. Okay, and this I negative, there is some counter and also present that is combined with iodine. Okay, Deshika, is this point clear that why the option B is the correct here? Okay, just please confirm, Deshika, are you done or not? Deshika. No, oxygen is not a living group. Okay, who told you about this? Listen, that if we are talking about a living group, you know which one is a very good living group? First of all, the complete hallucin. Iodine is a better living group over the bromine, okay, over the chlorine and over the fluorine. The condition number one. Or if let's suppose we are discussing about OH, so OH is never ever a very good living group. OH become the living group only when we are having this kind of group, that is a water. So water is a very good living group. Okay, so you can say water. Oxygen is not a living group. Be noted. Okay, Deshika. Okay. Okay, you are saying better nucleophile. So look at this. Noting something. This is my oxygen. Okay, and this is also my oxygen there. So like both the cases we are having oxygen, oxygen. Then how to check? So now there's a tie for the oxygen part, Deshika. Now check it for the negative charge. So O negative has a negative charge, but on the other hand, phenol is a neutral point. So neutral is better there as compared to the charged one. So that's why everyone wants to neutralize the charge. So charge be like I want to neutralize. So O negative attack first O as compared to the lone pair one. Okay, Deshika. Still any problem? Yes, please, Deshika. Okay, man. You just join. Okay, Dishika, I'm still okay. Okay, no. Okay, I'm asking a general question for you. Okay, it is a CH3 and a CH3. Okay, A and B. According to you, which one is stable? Hmm, Dishika? Okay. Oh, you're that much good now. Yes, please. Dishika. Got it? Okay, thank you then. So let's back again. So what we're discussing, right, that part. Hmm. So yes, between alcohol and ether, if we are comparing the boiling point, so definitely the alcohol is a bit has a maximum boiling point over the ether there. So what is the reason? Simple answer, hydrogen bonding is the reason. Okay. So if you have to compare between alcohol, so alcohol has maximum boiling point over the ether. So answer is what? Hydrogen bonding. Okay, because in alcohol there is a hydrogen bonding present. Now, this is the point number one. Okay, that's it, sorted. Let's back again where we're discussing about. Okay, so boiling point. So look at this, what is written here. The last difference in the boiling point of the alcohol and ether is due to the hydrogen bonding in alcohol. And due to the weak polarity in a CO bond, the boiling point of the ether is similar to the alkene system. Means if we are checking for the polarity, all the oxygen is present there, but in this case, polarity is not that much high. Okay, not that much polar, because look at this, like if you are observing something, there we are having a lone pair, and I hope you it's a band shape. And if you're checking for the kind of that is a dipole moment. So in this case, dipole moment is approximate around zero. Okay, not zero. I'm not saying complete zero, but it's like let's suppose zero, zero point some eight, some number have to be there. Very small value you can say. Okay, so just because of this, we are not treating the ether be like very good polar compound. Less polarity have to be there. Okay, so it's a less polar compound, and this is that much less polar that we are comparing that eth alkene, the carbon carbon double bond system, or the ether system, both have approximate same boiling point. Okay, now second point, that how about the solubility? Okay, the point, I hope the point number one is clear for you. Now the second point, if I'm adding alcohol into the water, okay, alcohol into the water, so it's simple that obviously the solubility is very good, hydrogen bonding is the reason. Okay, now the condition number two, if I'm dissolving ether into the water, so my question to you, still there is any kind of hydrogen bonding present? Oh, yes, please. Between ether and water, still there is a hydrogen bonding. And if which kind? Is it intramolecular? Is it intermolecular hydrogen bonding? Is it intermolecular or it's intramolecular? Which kind of hydrogen bonding? Intra. No, no, no. How it's intra, okay? Come on, it just don't compare the water, okay? Inter one. Inter one. Yes, very good, Batul and Lakshmi. Look at this. If you're observing, this is my ether molecule. So as we just discussed, ether molecule has no hydrogen bonding. Because you know already that which thing has hydrogen bonding, OH and a OF or a ON. Okay, so basically like you can compare H or some fluorine. Okay, I hope you're getting my point. That HF, HN or HO have only the kind of hydrogen bonding there. So means simply I'm erasing this. Okay, there is a no hydrogen bonding present between the ether. But if you to add the ether into the water, now they are having hydrogen bonding. Okay, look at this oxygen. Yeah, there's a hydrogen bonding present. So which kind of hydrogen bonding? Between molecules. It's not inside the ether. Look at this. It's a inter type of hydrogen bonding. Intermolecular hydrogen bonding between two molecular hydrogen bonding. So just because of this, that although boiling point wise, alcohol has a maximum boiling point. But if you are comparing the solubility point, so alcohol and ether has a almost similar solubility. I'm not saying same. I'm not saying like maximum minimum. I said that is almost similar. So means what is the meaning of this point? Almost similar. Let me just back again. Let's compare the data. Okay, look at this. See this, that if you're using butane 1-ol, it means alcohol, or if you're using ethoxyethane, same number of carbon, 4 carbon. Okay, same one OH, one oxygen, one oxygen. So I hope the mass is not the issue. 74 and 74. Okay, which kind of isomerism this is? Functional isomerism. Okay, look at this 9 and 7.5. So it's almost similar. So what is written here? While the solubility of both is almost similar. So answer is what? Hydrogen bonding is the answer. Look at this, that intermolecular hydrogen is bonding is present if you are adding the ether into the water there. That's it. This is all for the solubility part. So right now, till then, we discuss about uh, first of all classification part, then preparation part, and then physical property. Now the last part start that chemical properties. So in a chemical property of ether, as let's normally discuss about ether, how the ether is going to react there. Okay, again a general question for you. If you're having a COC, so some nucleophile came into the picture. Just think about it and then answer the question. Is it possible nucleophile attack here and this bond break and we are getting some CU and some nucleophile? Is this kind of reaction is feasible or not? Yes, of course. That's why see the difference, Patula, that in alcohol we are having 9 value, but on the other hand, ether there's a 7.5 something. Right? So what is the like uh, comparison wise, maybe like ma'am's 9 and 7 is a different point. Okay, try to understand the thing. What I want to highlight to you, that we come just discuss about ether has a very less boiling point. Let's approximate around the alkene there. But now the statement explaining here that how they are having a almost similar value. 7.5 and then 9 is not really that much large value difference. Okay, I hope you're getting Batula, okay? So, but yes, you are right that alcohol still has a maximum value, but approximate around the ether part. Yes, please. In this case, this kind of friction is possible. Okay, wait. Okay, this is water. Okay, and one more, this is water. I'm highlighting some number you can say that, okay, alphabet A and B. So, according to which one is a hydrogen bonding? Yes, please. Which one is a hydrogen bond? Is it A or is it B? B, right? I hope everyone you know the basic that A is what? A is a covalent bond. Don't say this is a hydrogen bond. It's a simple covalent bond. Okay, so B is a hydrogen bond. So what is it? This is my molecule number one. Okay, this is my molecule number one. And this is the molecule number two. So what is happening between two molecule? Okay, so between two molecule. Okay, point number one. So this kind of bonding is known as an inter. Okay, inter school competition, everyone you know the meaning of this, that there's a 2 to 3 school and they participate at some level and it's become inter school competition. Okay, like between some schools, uh more than one school you can say. Okay, now the second point is what? For example, let's just compare some okay, carbon, and this is nitrogen. O, double bond, positive charge, negative charge. O, NH. Okay, this is a molecule number one. Molecule number one. Let me just form one more. Carbon, nitrogen, O negative, double bond, like this, O and H. Okay, so now in this case, look at this is a molecule number one and this is a molecule number two. There's a two molecule. Okay, now look at this. Yes, there's a first possibility like the previous one, maybe this oxygen combined with this hydrogen, like the same hydrogen bonding intermolecule you can say. But look at this one more possibility there. This hydrogen be like, why we are moving outside if we are having a choice inside the molecule? Look at this hydrogen combined with this oxygen there. So if you are observing something, the red one or the one and two, if you are comparing, that one has a separate bonding inside the molecule, and the second one also inside the molecule. One and two has no connection between one another. okay, by the hydrogen bond. So this kind of bonding is known as a intra. Okay, so what is the meaning of this word? Intra means within the molecule, within the same molecule, like the interval between two molecule, more than one molecule, but it's in between, inside the molecule. So that intra within the same molecule there. Okay, like the famous one, orthonitrophenol or orthonitro, that carboxylic acid. Okay, I hope it's clear now. Okay, so let's just back again what we're discussing. Okay, so in this case, look at this. What we're discussing, it's not visible. It's not visible. First of all, if you're observing like polarity wise, it's the partially negative charge, partially positive charge, partially positive charge. Okay, so in this case, you can say the bond is not that much polar. We as we already discussed. So this kind of attack is not really feasible. Not really feasible. Okay, that's it. Now let's just back again. And now what we're discussing. Look at this slide. That chemical property, well, this is not visible because it's a less reactive compound because not very good polar, weak polar bond is present in a ether. Then it means ether is not going to react. So very good thing we are not going to discuss about so many reaction. Yeah, you can say. It's a plus point for the ether. There's a no so many reaction present in a ether. But you know, there is a every time the problem. Okay, so for example, if you're having ROR, there's some acid I'm using, let's say H positive. Okay, so oxygen will be like, oh, lone pair and you're H positive, let's attack there. Okay, and see what we are doing now. So we are forcing, although ether are not reactive, but somehow we are converting the ether into the reactive part. Now O positive. Oxygen will be like positive charge, how I can handle. So let's quickly break the bond. So simply this is how the bond break and we are getting ROH. Yes, this is how it's going to react. Okay, so let's discuss about the reaction as well, like how they are going to react. So this point is clear, and then the second point is what? That ether, this is written, ether can react to under drastic condition. That harsh condition, cleavage, high temperature, high strong acid if you're using, they can cleave. Okay, they can cleave, but generally they are not very reactive. Okay, so reactivity wise, not very good reactivity, but if we are having a choice, obviously we can go. So now let's start with the reactions of the ethers now. Wait, okay, I'm checking for this. This is going to be the very much important reaction, okay? So let's discuss about the reaction of the ether now. As we discussed, the reaction with the acid, okay? Reaction with HI. So what is happening? You are having some ROR, okay, and then HI is there. In this case, we are end up with a two kind of product. So first write the reaction, general reaction. Okay, so ROH and then RI. Two kind of product we are getting. So you can say this bond break. Okay, so like you know HI. So H has a positive charge, partial positive, and it's a partial negative. So this go with this and this go with this. ROH and I negative. Now let's talk about the mechanism part, how the reaction is going to happen or how the mechanism, all this thing. Okay. So a mechanism is not important, just try to understand the reaction only. So how about the mechanism part here? This is some ROR. Okay, again lone pair H and I. So you know very well, oxygen has a lone pair attack here. Okay, so partial positive charge, partial negative charge, and then in this case you're having I negative present now. Okay, so it's a R O H positive ion generated, and this is the good living group now. So again, iodine come into the picture. Iodine simply attack here, and this bond open up, and we are getting that R OH plus RI. So that's it. This is all for the mechanism. Okay, so this is a normal general mechanism for the reaction. Now, important is what? How to identify the product. Okay, so let's discuss some questions from this part and the topic will be clear for you. For example, look at this. Oh, one more thing I want to highlight, that in this case we are going to follow the SN2 mechanism. Okay, SN2 mechanism. Normal reaction. Now let's solve some example. Then and then we are getting like actually how to decide the product. So This is a kind of question for you. Let's suppose this is a CH3 and a O and a CH3 and a CH3 and CH3. Okay, if let's suppose I'm using HI, there's a two possibility. The possibility number one, maybe that the bond cleave from this side, the pink one. Okay, so according to the condition number one, let's say the condition number A, the I negative part go with the CH3, so it's become CH3 and I plus, or it is a CH3 and a CH3 and a CH3 and a OH is there. Condition number one. Maybe the condition number one, two, no, it's going to cleave from here. Okay, I hope you are getting my point that this is how this point separately break. It's a B there. So in this case, this is a CH3 and this is a OH now and plus that CH and a CH or iodine. So like both possibility can be there. But my question to you, like which one is the A or B? Which step we are going to follow here? Think about it, try to answer the question. I will explain definitely, but at least once try to answer the question. Like according to you, A is the feasible one or B is the feasible one? Okay. So yes, everyone is right. Option A is going to be the correct answer. Why it's going to be the correct answer? Because it's a SN2 mechanism. As I just told you about this, it's a SN2 mechanism. So if you have to follow the SN2 mechanism here, okay, so what we're getting simply that obviously if iodine combine here, try to understand actually what is happening. If it is a SN2 mechanism, so we have to follow the less hindered side there. So iodine be like, no, I can't go because I am going to follow the SN2 mechanism. So I have to attack on the less bulky side. This is a less bulky side. The green one is the less bulky side. But on the other hand, look at this. This is a more bulky side. So iodine is not going to attack on a yellow part. Okay, option A is the correct answer. Okay, but let me change the statement. What if the direction follow the SN2 mechanism? Okay, for this answer A is the correct one. But what if the equation follow the SN1 mechanism? Then A is feasible or B is feasible? Okay, because of course we are going to discuss about the reaction mechanism in between sometime. Yes. My question is what if in the reaction we are following the SN1 mechanism? So A is more feasible or B is more feasible now? Okay. B. Okay, obvious. So listen, that in the same reaction, if I'm following the SN1 mechanism, then I have to go with this answer. Why? Because now that my tertiary carbocation is going to be the stable one. Okay, so that's it. Hence, this is the correct answer. B is the correct answer. SN2 less bulky side, SN1 more bulky side we are going to consider. Okay, so that's it. This is all for the reaction. Now let's discuss some more questions. Okay, this question part is really important. These are some PYQs you can say. So let's discuss some question and please apply your common sense, okay? If I'm using HBR, so you have to identify the physical product, okay? Like which option is correct, simple. So the condition number one, OH CH3Br. Condition number two, yes please, A or B. Which one is the correct answer here? Of course, Dashika, I will take, not an issue, okay? Yes, very good now, okay? So in this case, ma'am, you're not able to understand which what we have to follow. Be noted. If benzene is given, so every time the bond breaking from this you can say position, never ever follow the yellow one, because we discussed it's this thing so many time. It is a sp2 hybridized. There is a partial double bond character, difficult to break. So that's why this is not feasible. Okay, partial double bond present here. Okay, that's a simple answer. So option E is the correct answer here. Okay, let's solve some more questions. Okay, one more question, please. Okay, answer this, please. Okay, this is the last question. Some reaction we are left that we are going to cover in the next class. HI. Okay, heat this. Some options. Okay, just answer the question. Till then, you can try. I am rating the answers. Which one is the correct answer? Okay, see. First, just solve this question. Then, do you know why I'm considering this question? Maybe some point important. You guess A. Okay. So let me tell you, guess is very bad. Okay. A can't be the answer. Come on. I told you so many times. If benzene is there, that bond is not definitely going to break, right? Okay, Shiva. Okay, Neharika. Okay, Jatan. Anyone? Option number D. Okay. Kanhai. Okay. D. Okay. So let's see what is the correct answer then, okay? So first of all, if you're breaking this bond, come on, please don't do this, okay? Iodine connected air, not possible. Iodine connected air, not possible. So option A, option D, totally out of the race. Okay, now in this case, that the condition number one. If you have to break the bond from here, okay, so you are getting iodine may be connected here, okay? Like this is a common point. Wait, I'm highlighting this. This bond is definitely going to break from here. So OH, this is there's a tie between B and C option. Now, how to decide between that we are going to follow A or B, like B and C, which one is the correct answer? So now let's make a knot, okay? Let's not an important point here. So first of all, write a knot at the very top. Although in this section we are going to follow the SN2 mechanism, but if stable carbocation form, we can go with SN2. SN1. Okay. So what are the stable condition? I will write that point as well. I guess it's not visible, right? Okay, first noted down the point, okay? If stable carbocation formation is possible, we have to follow SN1 mechanism. Okay, be noted. And what are the important condition like formation of stable carbocation? So like tertiary one, the condition number one, if there is a possibility, or the condition number two, that phenyl carbocation. Okay, if this kind of possibility there, yes, of course we can go with this. So let's just back again toward the question back here. Okay, here. So look at this. If I have to break the bond, the blue bonding, okay, so it's a stable carbocation. See this, this is a stable carbocation. And one more, one plus point as well, that it's connected with the benzene. Okay, then according to you, which one is the correct answer? No, option B is the correct here. Okay, so I know exception is always there. Okay, yes, of course. So, Batula, first of all, it's also a very good point. If you are able to eliminate the options, like this is a correct or incorrect, okay, it's a huge achievement if you are having four option and you are able to eliminate at least two option just by the common sense. Okay, soon you can decide between the left two option as well, but I hope the my point is clear for everyone. Okay, so is this point clear? We are just left with 2 points, that epoxidation part and electrophilic substitution. Okay, because right now if I have to start, so it will take 30 minutes approximate. Okay, so let's discuss in the next class. Okay, although my goal be like how to finish the chapter, but still some topic left. Okay, so yes, it's your turn now. Any problem, any doubt, just ask. Okay. No, according to me, the everything fail. But that intuition has never ever be the wrong one. Okay, if your sixth sense is very good, so you can do anything in your life. Bookish knowledge is not enough to do something. Okay, Shiva, if you're not having that, and who's asking what is the name? Dashika. Yes, please, Dashika, what is your doubt then? Okay, if you're not having any doubt, then you can leave the class, okay? If you want to ask something. So, Venom, what is the moral of the story? And what is your real name? Welcome, Batula. Yes, please, Dashika, if you are there, please ask. Decomposition. Miyol, this is your real name. Maybe you really like Star then. So, decomposition, like for which part you are asking? How to find out the order? Decomposition. Chemical kinetics, right? First order, okay. Okay. Then Venom is okay, okay. Like which point you want to ask? Like concentration point? Sorry, I'm not getting. Like any particular point, temperature or concentration? Which thing? The rate of decomposition, order of decomposition. Because according to me, decomposition is the topic of the electrochemistry. Okay, in electrochemistry, sorry, chemical kinetics. Okay, there we're discussing about the order, first order. So this one, okay, order of increased deposition. She is asking for the deposition of the metal in electrochemistry. Okay, 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 okay. Got it, got it. Yes, please. Okay, wait a second. Just let me know if you this you are saying. For example, if let's suppose I'm using a carbon rod, okay, cathode, let's say, and this is anode. So you mean to say, if let's suppose I'm using H2SO4, okay? So in the ion, H positive present, SO4 2 negative present. And if I'm using water as well, so H positive present or O2 negative present. So it means if let's suppose we are discussing about the electrolytic shell, so in this case, cathode has a negative charge, anode positive charge. So toward anode, both ion can be go, that is SO4 to negative or O2 negative, right? And for the cathode side, H positive also can move, one choice only. So how to decide between SO4 negative or O2 negative? This is your question. And just send me your problem, okay? You can say. Okay, just connect me on the WhatsApp, okay? Maybe I can take your problem. Okay? Dashika, just do this. Let's finish the class. Life is not full of problem. Just enjoy the life. Better to finish the life. Mm, better to enjoy the path. I'm not a very good thing point, but I hope you're getting my point. Anyway, thank you so much for joining the class, and Dishika just connect with me, okay? Personally. Thank you so much, everyone. Thank you.